This is the Chem 1 lecture over fission and fusion. So today we're going to look at two really big ideas in nuclear chemistry and nuclear reactions, fission and fusion. And you're going to really get a good scale of the amount of energy involved in these kinds of chemical reactions. So all the energy that gets released in nuclear reactions can be calculated using Einstein's equation, E equals mc squared. Now, we will not actually be using this to calculate energy, but just understand that we're talking about a huge scale here, orders of magnitude more than any chemical reaction would release. The first big idea that we're going to talk about is fission, which is actually the weaker of the two, but it still relates a bunch of energy. So fission is the type of nuclear reaction that takes place when a larger nuclei splits into two smaller nuclei and releases some energy. Fission is generally initiated using a neutron. So a neutron comes in, hits a stable nucleus, which turns it into an unstable nucleus, which then splits apart, releasing at least two smaller nuclei, and then a bunch of neutrons that can then go on and repeat this process to other unstable nuclei. So since we use a neutron to start fission, as you can see here, a neutron comes in and hits a stable piece of uranium, which turns it into unstable uranium, which will then split apart. It will then also release three other neutrons. In other words, I started with one and I've now made three. So if you put a bunch of these starting uranium-92s that are stable together, you create a chain reaction, because each of these three on the end can then go hit a stable piece of uranium and just repeat this process over and over and over again. If you have enough nuclei close together to cause this chain process, we say that you have a critical mass, that your fission has turned from a single occurrence into a chain reaction. So here's your textbook definition of a chain reaction. When one nuclei undergoes fission, it releases enough energy and enough particles to cause other nearby nearby nuclei to undergo fission, and so on and so on and so on, and you get huge amounts of energy released very quickly. So fission has some very specific fuels. The most common currently used is that uranium-235 that you've seen in a couple of pictures. It is still it's a fairly rare fuel, but it is it's the most stable and most common that we use. Only certain isotopes can undergo fission. You have to be able to be kicked off using a neutron. So some examples are uranium-233, 235, and an isotope of plutonium-239. There's several other isotopes. Thorium is an element that has several available isotopes. But just like any other metal or oil or natural gas, it is technically a non-renewable resource. So once we use it, it decays, and it's very difficult to get back. So fission can either be controlled or uncontrolled. If it is uncontrolled, you get the atomic bomb. The two cases where it was ever used was Little Boy and Fat Man. The bombings in Japan that ended World War II. I'm not going to get into all of the details behind their usage and their development, but there's some really brilliant stories behind their development and how we kind of discovered how we can attempt to utilize fission. I highly encourage you to go do some reading about some of that history. It is very interesting to hear about the opinions of people both who were working on the project before it was used, and then how, after they saw the devastation of the atomic bomb, how they then felt about their own research and their own discoveries. We have since that time in 1945 kind of, learned how to control our fission better. So the same type of reaction that was used as an atomic bomb is now used in nuclear power plants, using something called a moderator or a controller that essentially slows down the chain reaction so that it doesn't all go out at once like it would in a bomb. It still happens, just much, much, much slower, and we can absorb a lot more of that energy and transfer it and use it to power homes and turn into electricity, etc. So just a brief rundown on nuclear power plants. We're not really going to ask you any questions about them, so don't necessarily feel like you have to understand them. I just like to include this slide because it's good information as we start to look into a world where we have to rely less and less and less on natural gas and on oil. Nuclear power is a very big option. It's a very good option. It creates no air pollution, unlike the coal and burning oil and natural gas, and it produces much, much more energy than either of our current processes. Essentially, how it works is you have a big old container, a containment structure inside there, and this little box right here is your nuclear fuel. You start the process using these control rods to control the speed at which your nuclear reaction happens. All of this red color that you see is water. And this water absorbs energy and gets very, 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 very hot. This tube then connects to another set of tubing that is also full of water. Now, it's very important to understand that this red water is very, very, very radioactive. So it is controlled and it is constantly pumped through and recycled. It never leaves, or should never leave, this contained area. The way that we transfer the energy is we let the heat and the high temperature of the red water boil this blue water. That way there's never any radioactive crossover, but it's just energy, it's heat. It's like having two hot pipes next to each other. The heat from one then bleeds out and heats up the water around it. It'll eventually heat it up so much that it turns into steam. It goes through the steam pipe. It turns the turbine and generates electricity that then gets pumped out through power lines. As it emits that energy, it turns heat into mechanical energy in that turbine, so it's actually cooling down. So it turns from steam back into hot water, in order to ensure that it doesn't, this blue system doesn't get overheated. There is a third cooling water system that is there just to absorb any excess heat from the blue water before it gets pumped back into the system to reinforce, to be reused. Again, I went through that very, very quickly. Your teacher would be happy to kind of sit down and go through it a lot more slower and answer your questions if you'd like, but don't feel like you have to memorize all of these pieces. I promise we won't ask you any questions about how a nuclear power plant operates. It's just a really good example of why fission is still really, really important to understand. We still use it today. So some of the biggest concerns about nuclear power, why can't we just go all in on it? Well, because fission creates very highly radioactive byproducts. So yes, we get a lot of energy out of it, but obviously we get a lot of radioactive waste. All of the water, obviously the red water, and in some cases even the blue water, also becomes radioactive. Therefore, it is another source of radioactive waste. So not only do you get these highly radioactive products out of the fission reaction that you then have to deal with, the water itself becomes radioactive, and now you have a lot of radioactive waste. So you kind of have a trade-off of, well, there's no pollution to the air, but there is this very highly radioactive byproduct that we have to deal with. We have ways of dealing with this. We have suggestions and ideas for dealing with this that I'm not going to get into in the video just because we're trying to keep it short. Again, I highly encourage you to come in and talk to us. so that we can give you more information about the benefits of nuclear power and how realistically it's a very, very good and very, very safe option. A lot of the opinion of nuclear power is it's good, but there's a lot of danger. But we have, over the years, become very, very good at controlling it and reducing and minimizing a lot of those dangers. The biggest draw is, of course, this nuclear waste. So, overall, are nuclear power plants safe? Yes. The short answer to that is yes, 100%, absolutely. They are very, very safe. In all of nuclear history, there have been 3 accidents. If you compare that to other modern forms of energy like coal or oil or natural gas, that is one of the safest types of energy. Yes, there have been 3 incidences where there were issues. One that pretty much everybody knows about. In history, obviously, Fukushima was fairly recent. However, that being said, if you look at it in terms of history, they have done less damage and caused less fatalities than some forms of energy do in a single calendar year. Not going to burn through all 3 of these stories in this video, again, because we're trying to keep it brief. There was one incident in 1979 in Pennsylvania on 3 Mile Island. It was an accident. However, there was no real impact on the environment or anyone. No one got sick because of it. In fact, it barely even registered on background radiation. It just caused a stress. It caused a fear. That fear was then reinforced 7 years later when Chernobyl had its issues. It is currently still the largest nuclear accident to date. We are still trying to understand a lot of the fallout from that. But we have, since 1986, dealt with the majority of the lasting safety implications, including recently a brand new giant concrete tomb in order to prevent any more fallout or radioactive material from spreading. Most recently in 2011, there was an earthquake and a tsunami off the coast of Japan that hit the Fukushima nuclear plant. It's a very interesting story behind it. The short story is the nuclear plant was designed to last an earthquake. It was designed to last a tsunami, not necessarily both at the same time. We have since dealt with a lot of the issues. We are still learning today that there are some lasting effects that we're trying to get to and deal with. However, there was no deaths reported from the actual nuclear accident. All the deaths involved in the Fukushima incident were actually caused during the evacuation or from the earthquake and tsunami themselves. So while all of these sound very dangerous, other than Chernobyl, there were no actual loss of life due to the nuclear plant itself. So long story, there's a lot of detail in here, and we would be more than happy to discuss these with you in class. But are nuclear power plants safe? The short answer is yes. So now that we've talked about fission, let's talk about the other side, fusion. A day without fusion is like a day without sunshine, because if fusion didn't exist, the sun wouldn't exist, and it would be very, very cold all the time, and life in general would not be here. Fusion is when you take 2 smaller nuclei and fuse them together to form a larger nucleus. So fission, when you take a big thing and split it. Fusion, you take 2 small things and make them into a single bigger atom, and when you do that, you release much, 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 much more energy than even fission is capable of. So examples of fusion, natural fusion is the sun. It takes place continually. The temperature at the core of the sun is between 10 and 15 million degrees. Fahrenheit, which, again, this is science class, so we focus on Celsius, would be 5,500 degrees Celsius. It's so hot and there's so much pressure that hydrogen atoms slam together, creating helium and releasing energy that travels about 8 minutes through space to get to Earth. On Earth itself, we actually have done fusion before. We have never done it controlled, and that's very important, but we have done uncontrolled fusion. The hydrogen bomb, which was developed as a successor to the atomic bomb, is based on fusion instead of fission. It was also much, much more devastating, and luckily it has never, ever been used in any kind of conflict. So can we do controlled fusion on Earth? Well, we have the fuel. It's really simple. It's hydrogen. We need hydrogen, and we have a lot of that in the water. You can take water and break it down and get deuterium and tritium, two slightly heavier isotopes of hydrogen that could then be used to start fusion. The problem is we can't control it. We don't have the environment that the sun does. Obviously, the sun is 5,500 degrees Celsius. No material on Earth can realistically control that amount of temperature yet, because essentially you have to be able to control plasma. We don't have a physical material that can touch plasma, but we've been making huge leaps in research into ways that we could potentially control plasma. This is a YouTube video here that is a kind of a cool little history. Talks about the biggest bomb ever detonated on Earth. It was called the Tsar Bomba, and pretty much led to the bannings of atomic weapon testing in most places around the world. So on that note of perfecting the method, it is really important that we continue this research because fusion releases no atmospheric pollution and it doesn't produce any nuclear waste. The radioactive things that are created by fusion are very short-lived. They, in a blink of an eye, stop being radioactive. So you don't have to worry about long-term waste disposal like you do for fission. Again, there's no pollution, just like fission has. It's a nuclear reaction, so you're not creating CO2 or methane or any greenhouse gases. And in fact, fusion is very, very safe because should something go wrong and your generator have a problem, well, it's going to lose its heat. There's not going to be any sudden explosion. It's just going to cool down very, very quickly. And as soon as you cool down, your plasma turns back into a gas and all of the system shuts down. So it is actually very, very safe in the sense that we wouldn't even have to necessarily worry about any real nuclear accidents. In that vein of where's our research going, there's several very prominent ideas for what we could do and types of reactors that we could build, two of which are listed here, the Tokamak and the Stellarator, both of which are currently in development and research. The Tokamak, a modern, up-to-date version based on our research, is actually going to be finished in 2021, and on paper will be in full operation by 2035 and will be able to generate energy in Europe. Another one that is, again, currently has actually been built and completed and is tested is the Stellarator reactor titled the Wendelstein X7. They are very, very expensive, but they're very, very promising in terms of future designs. We've turned them on, and we've had successful tests with them as early as 2016. Realistically, as quickly as our research is developing, don't be surprised if within your generation you start to see fusion becoming the biggest source of energy for our world. As I've said a few times throughout this video, we highly encourage you to come talk to us. Fission and fusion is a very interesting topic. Basically, the big idea is you need to know that fission, you take the big things and split them up. Fusion, you take the small things and you put them together, and overall you get lots and lots and lots of energy. As always, if you have any questions or if you want more information, feel free to come to us for tutoring. And that brings us to the end of Fission Fusion.